the most important model findings? What are the most important model findings? And then how might they provide insights for the decision? Now, some of your findings that you got, your results, how can they provide insight for decision? Can you use your findings to bring out insight for decision in a particular location? And then for what period of time were impacts measured? So what year are you considering? Some of us, and I saw that you have a data from 2018 to 2020. Is it 2023 or 2024? 2025. That's a very good time series data. For which location? Nigeria. Is it measles? Okay, measles. So, yes. So you have that one is a national data, and that means it has collapsed all the states in Nigeria together. Now, for you to really do a very strong work that can influence, you can do it at national level, but it's also good that you look at it from sub-national, at state level, because you cannot just put all of us together. Now we can see Nigeria as a whole, but we also want to see what is going on in these states. People are also interested what is going on in Oyo Ekiti, like local government level, even polling units. We have about how many local governments? 774 local governments in Nigeria. If you are looking at each of them like that, you know, that's a very, very good. That'll be a very good work to look at. Yes. Next slide. Now, what assumptions were tested across a range of scenarios? I was saying different for your scenarios. There are different assumptions, assuming that you are working with measles. Like I said, you can look at it from the point of view of the percentage of vaccination coverage now in a particular location. Now, because for measles, we said last week that what's the R naught for measles? Somebody can remind us. I said it over and over again. What's the R naught for measles? No, it's a range between 12 to 18. 20, 12 to 18. Yeah. So now it depends on the location you are. Now it means that if I want to, like, if you want to eliminate measles, we have to look at the R naught and the herd immunity. Let's assume that if our R naught is 18, let's even assume it's 18, it means that one infected person can provide 18 secondary infection. That means you can infect 18 persons. That's the least. So it also means that now the HIT, which is the herd immunity, which is what determines the immunity of the population. So the HIT is equal to 1 minus 1 over R naught. So R naught there is 18. So 1 minus 1 over 18 is what? What is 1 over 18? Can we divide it? 1 divided by 18, what is it? 1 divided by 18 is what? Daniel, can you do that? 0. Okay, 1 minus 0.005. What do you have? Okay, 17 over 18. So divide it and multiply by 100. Divide that and multiply by 100. What do you have? 94.4. So it means that now for we to have elimination of measles, we are supposed to vaccinate at least 94.4 of the target population at risk. And by WHO data that we saw recently, they said it's only 46%, around 46% of Nigerians have been vaccinated. So which means that measles is still endemic. Are you getting me now? So it means that the RC, we have RC. and we have R naught. Now, if you are doing modeling on measles now, you should not be talking about R naught because we already know the R naught. What we want to know now is the RC of different places. The RC is the effective reproduction number. Now, effective reproduction number, what's the difference? Let me not even define it. I've been teaching you all these days. I should be able to ask you questions. So what's the difference between effective reproduction number and basic reproduction number? Yes, anybody? Effective reproduction number and basic, what's the difference? Yes? All of you are doing modeling, you better start. I'll call you now. Some of you that have been writing, no, last me. Relax, I'll call you. I want some of them to answer me first. Yes? You have been writing models, you have published papers. Yes? What's the difference between effective reproduction number and basic reproduction number? Yes? Here, come. Give me mic. Give me mic. It's part of the class.
For me, I think the major.
You think, or you are sure?
Okay, I'm sure.
Okay.
The major difference is that when we say basic reproduction number, you assume that that population is totally susceptible than for effective.
Are you assuming, or that is what it is?
That is what it is. It's
Okay.
totally susceptible.
Okay.
Then for effective, then you're assuming that the population is not susceptible.
No assumption now.
Okay. Okay, sorry.
In reality.
Okay, for basic reproduction number.
For basic reproduction number,
the population is totally susceptible to that disease.
Okay, then
for effective
effective reproduction number. Yes.
The population is not totally susceptible.
So what kind of population do you have?
No, what I'm saying is that like the population of interest.
I know what you are saying. So what kind of population do you have when you say they are not totally susceptible? So what are they? How do you define that population, the population at risk for effective reproduction number? Who is going to help him? Some of you are started checking ChatGPT. Okay. ChatGPT may lie to you, so you come and tell the lies there. You'll be in trouble. Okay.
Good morning, sir.
Yes, sir.
Okay. R naught is talking about susceptible people, and at that level, people are not infected. People are not no intervention. But when we're talking about RC, that situation whereby we already have a disease, we have a burden, maybe we deploy intervention, we have a policy to control them. Then we'll look at how those policies are playing, whether we are going back to.
So this man is a public health man, so he's giving you the full explanation. That's good. Yes. So, but there's something that is missing in your own. You are close, but something is missing. Yes, who is going to help him? Yes, sir. You are close, but something is missing. Yes.
Actually, I will say it in a simpler terms. R naught deals with the transmission, measure the transmission of the disease, while the RC controls the transmission of the disease.
Yes, you are also moving around. Now, when you say that, I mean, R naught, you are talking about the average number of new cases, due to in the presence of totally susceptible population. But for RC, you are talking about both susceptible and non-susceptible, because, like you said, intervention has been put in place. So that was why I was saying with population, both susceptible and non-susceptible. And that's why I said, and I said, how do you define it fully? So you have to say both susceptible and non-susceptible. Because as people are being born, do you understand? They are susceptible, and then as people are getting vaccination, they are becoming non-susceptible. Because you have introduced an intervention. So that's the difference. So in that situation, you find out that if it's not everyone that is taking the vaccination, the RC may still be very high, even though there is an intervention. And that was the case of the students. There are two students working on that. I mean, okay, one is undergraduate, and then there are few of them like two masters, and one PG working on measles in our center. And one of them, two of them has discovered that RC is around 2.9 for a particular state, Nasarawa. And then for another state, RC is around 1.5 or 1.9. So you find out that, you know, people are still getting infected, even though there is vaccine, right? There is vaccination, but people are still, and the reason is because there is vaccine hesitancy. Some people are not taking the vaccine. Some people have different kind of beliefs on the vaccine. Now, Lakshmi, do you have addition? Can you give her a mic so that we can project our voice?
From the primary infectious person, the first individual, when we consider it to be like there is no immunity and no interventions.
Yes.
And when we talk about over a period of time, when we see then when the infection starts spreading out, then the recovered classes also come into the picture, and also the immunity and the interventions, the human also intervene. And that is the effective reproduction number that can be measured in the proportion of the susceptible, because susceptible keep changing over a period of time.
Yeah.
Is that so?
Yeah.
Okay. Thank you.
So now the question again is that, is a full range of uncertainty around key parameters explored sufficiently? Now, if you have a measles model, what are the key parameters that you can mention? Just a simple measles model. What are those key parameters in that model? Anybody? Some of you are in measles group, you should be able to talk. Yes, for a measles model, what are the key parameters that you can just give us one or two of them? Yes. I'm waiting. Okay. If I close my eyes and open it, I'll call at random. So you better don't let me close my eyes and open it before you raise up your hand. I want to close it now. Okay, where? Oh yeah, let the person talk now. Give him the mic. Unmute yourself and talk to us. Thank you.
Okay, hello. Can I be heard?
Yes.
Hello.
Is there anybody that is ready here? Okay. Just one of the parameters in measles model. I'm coming.
Hello.
Just mention one or two. Okay, no, that's
We
a
have
variable,
recovery,
not a parameter. Parameters
that
moves within the
we
compartment.
will have the recovery, we will have the infection, we will have, I mean, the process of infection will be there. We also have
vaccination rates. Okay. The cause of infection is combined with many things. Is both the transmission rate and the infected compartment. Yes. Latent period. This doctor is getting something. You are trying to be a modeler. Don't worry. Okay, go ahead. So, online man, can you talk to us? We are hearing you, please.
Yes, please. You can hear me.
Okay. Yes. Loud and
I'm
clear.
saying, okay,
So what?
okay. So definitely we will have the infection rate. Probably we will have the force of infection that will
What do you
consist of the contact rate from
Okay, maybe
either
it's stopping the
the
transmission rates.
hello.
Yes.
Yes. So
Yes.
we have the contact rates, we will have the force of infection, we will have the recovery rate. If we are going to do intervention,
Recovery.
then definitely we have a vaccination rate as well. Thank you.
Vaccination, okay. Right, thank you. Now, if you are having vaccination rates now, and you have and you have let me put it like this. Okay, maybe you have vaccination rate or proportion of people vaccinated. Are they the same? Vaccination rates and then proportion of people vaccinated. Are they the same?
No, please, they are not the
If you
same.
are saying no, I want you to answer me. Raise up your hand and answer no, and then you tell us why. If you are saying yes, we are learning. That's the way to learn. Don't be afraid. If we miss it, we'll correct you. So if you are saying no, yeah, okay, tell us. You said no. So why?
The reason why I said no is that when we talk about proportion, we're
Okay.
just talking about part of those people that are vaccinated. That's proportion. So when we talk about rate, we are talking about how well is that vaccination. That is the effect of that vaccination on them.
Now, if I say, listen, don't sit down. You have not really given me a baby there. If I say proportion of people vaccinated, right?
Yeah.
Can I say that the value can be, okay, what can the value be? Let's say alpha is proportion of people vaccinated. What can alpha be? Alpha, just give me an example. Alpha would now be what?
Alpha can be 1 minus proportion of people that are in susceptible class. Let's say
No,
in a
just give me a value. Just give me a value.
Okay, for instance, let's say in a susceptible class, we have 1,000 persons.
Okay.
Now, out of that 1,000 persons, like 500 were vaccinated.
Okay.
So that's just proportion of people that are vaccinated.
So would that be alpha? Alpha will be what?
Portion, that's portion of people that are vaccinated.
No, don't talk. Value.
That's 0.5.
That's 500 persons were
500.
vaccinated.
500. Okay, if it is rates, wait. If it is rates, what do you have? If it's
0.5.
vaccination rates, what value?
The value will be between 0 and 1.
Okay. Now, yeah, thank you.
Yes.
Now, we usually mix that up because now when you say proportion, you are talking about fraction and you are talking about probability and must be between 0 and 1. Are you getting that? The space of the value for proportion is between 0 and 1. Now, the space of value for rates is between 0 and infinity. That's the real number space, R plus. Now, you see, when you are doing this is very important. You know, you are learning what's it called? Model fitting. Now, in model fitting, if you don't know the space that your parameter is, and you want to use an optimization method to fit either least square or maximum likelihood or Bayesian, and you don't know the space your value is, the parameter that you are talking about is, then you will find it difficult to be able to get the right. In fact, you may run it as many years as possible. So that means that you must, from day one, when we say proportion, you must know what proportion is and what capacity of number space proportion can take. Can only take between 0 and 1. So when you say rate, it can take between 0 and infinity, positive infinity. So which means it can take even 1 million. It's a rate. right? So there is difference between rate and proportion. Are you getting me now? So when you say proportion, we are talking about between 0 and 1. So if I place my value, maybe an assumed value between 0 and 1, because like when you want to do your estimation, you will place a guess on your parameter value. When you get there, I don't know when it's going to teach again, you place a guess. So it is that guess that your optimization tool will work on and give you a particular value. So if you don't know the space of the numbers you want to, then you are going to be in some trouble. So you have to know if you take a proportion, if you are talking about rate. And then number 2 is also that when you talk about parameters are always influenced by uncertainty. So you must not have your parameter fixed. Are you getting me now? I've said it over and over again. Don't have your parameter fixed. Have it as an interval. And then you can now say this is the baseline, the one you use for your model that works for you. Are you getting me now? So that one may not work for another state if you are using another state. So you must be able to, you create a parameter space because parameters are influenced by uncertainties. So you have to put them in a range. So we now said, do key model results range change qualitatively with the observed range? These are questions you have to also look at. Now, if you have a range, maybe a parameter is between, you have a parameter between 1 and 15. And then you want to check how each of those parameters are changing when you change the parameter values, how they change the behavior of the disease. Now, ensuring transparent collaboration. So I said the other day that now model projects require contribution from various multidisciplinary teams, modelers, epidemiologists, disease or intervention subject matters, policymakers, social scientists, program managers, and local experts. Now, all of these are going to make contribution into what you are doing, because some of them goes to the field. Me, I'm a mathematician. I may read some things. I may get understanding of some things, but there are some people that they see the patient every day. I remember when I was doing when I was rounding up I did something on malaria cysto, modeling malaria schistosomiasis. And then at the University of Ibadan, the HOD said, this thing you did is not possible. He said somebody in UCH told him. So they stopped me from presentation. They didn't allow me to present. So eventually my supervisor called me and said, are you sure of what you have done? I said, why not? I'm sure. He asked me 3 times. So, but before then, I have to consult different people. That was when I went to her. I asked her some questions. I think they were in that small health center then. I mean, is there any relationship between malaria and cysto? Even after I've read some things, I consulted some people, and eventually I got some information that validated what I had read before, even in literatures. Are you getting me now? So you need input from epidemiologists, disease or intervention subject matter experts, statisticians, policymakers, social scientists, program managers, and local experts. And you know, one thing about cysto is that when somebody has schistosomiasis, especially, you know, cysto is driven by worms, schistosome, worms, and majorly people that live around the riverine area. And if you have cysto in your body and you are treating malaria, you have, let me give an instance now. You have cysto in your body, but because they share the same symptoms with malaria. So you'll be seeing symptoms, fever, and all of that. And you also have malaria at the same time now. Because there are people, there is what you call polyparasitism. Polyparasitism means that the existence of different parasites in your body, more than one. There are people who have that kind of condition. So, which may end up in co-infection. So, you find out that in certain places, that kind of issue happen, and then the person is treating malaria, Malaria will not go if you have Chisto and you are treating malaria. You have malaria and you have Chisto, and then you are using ACT only. It will not go. So it was in the model we discovered that when you use praziquantel, which is meant for Chisto, malaria will go down. So there are certain immunological influence, call it Th1 and Th2. Let me not go into that biology this morning, but now so the two Th1 and Th2, one is the two of them are responsible for immunity for malaria, against malaria and against Chisto. So if Chisto is there, it will not go if you are using ACT. So the model was able to express that, and they had to call me back to come and finish my work, because I sent some papers on that work and it was published. Now, what I was saying was the fact that at the time I was doing it, when confusion came, I consulted people, you understand, who are in the field, who could confirm some of the things we were talking about. So clear definition of roles and responsibility at the outset of the project. Strong internal communication and dissemination planning ensure stakeholder engagement and transparency throughout the process. So that means from the word go, when we wanted to start our project in the CAMDA, PSG, and all that, we had meetings with people in NMEP. And then they gave us their operational research agenda. We took out questions from there. Now, the questions that the PhD students and master students, most of the students in CAMDA are answering are based on things from the NMEP, not just publication. The questions they want modeling to answer. So we're working with them. We went to Abuja, we had meetings, we came out, we brought the question back home, and then we started working on, there was no students that did anything on malaria or Chisto or any disease that will not go through their strategic plan. You have to know about it. In fact, that's the first thing I will give you to go and read. The NMSP for Nigeria, the one from 2021 to 2025, every student have it in his head. You have to know about it, because that is going to guide your project from the word go. NMSP, National Malaria Strategic Plan. Because if you are working in Nigerian space and you cannot speak the language, then what are you doing? So we make sure that you are, even if you are doing cholera, I will find the strategic plan for cholera. I have brought the guy in charge of cholera in the whole of Nigeria to Ikamda to give a talk, because they are the one there. We will understand them to be able to develop the model. So we have people working on Chisto. The person working on Chisto, Fibre genital schistosomiasis. Now, there is this man that was that is working in the space of Chisto, Professor Epo, and some other people like that. So when Ronke wanted to start our work, I went to him. I said, do you have questions that you want modeling to answer? And then he sent me a question, about 2 or 3 questions. And that was what she did. And she did it very well. She was able to answer the question that is operational. That's the way modeling. So now when they want to do anything, they contact us, they put us in their group. Let's work together. Because you can speak their language. So I think that's the way to do it going forward. Now, mathematical modeling, models can support vaccine or control intervention policy, not by supplying verified facts, but by providing decision makers with a structured way to explore plausible scenarios. That's one thing it does. It may not be able to give you verified fact like 5,000 people exactly, but it will give you like given plausible scenarios, clarifies assumptions, and assess the implication of alternative vaccine or control intervention or treatment strategies. So you can have different strategies. You'll be able to guide you on which one is the one that can give you optimal results. Then they can be powerful tools to support immunization decision or control intervention decision, particularly when used alongside local knowledge and other decision support tools. Now, by fostering collaborative engagement, clarifying assumptions, and embracing the iterative nature of modeling, stakeholders can better harness these tools to improve health outcomes. So it can help to improve health outcomes and inform effective control strategies, control intervention strategies. So what are models and how can they help us? So there are tools that simplify real-world system and help us better understand disease pattern and the impact of different vaccination strategies under various scenarios, such as how well different vaccination plans might work, depending on when and how vaccines are given. How will this vaccine work, depending on when this vaccine is given and how it's being deployed. And then health decision makers can use models to support their choices. You want to make a choice. You don't know how the choice will save life or how much it will save life. You don't know. And you need to make that decision now. So models can guide you. Their choices about vaccine introduction and policy around vaccine use. And then models can provide important information such as how many cases and deaths a vaccine could prevent. How many cases, how many deaths will be averted if we use this vaccine? If we use 80%, if we use 60%, how many cases will be averted? How many deaths will be averted? And then the threshold required for heart protection can also help us to know HIT, our HIT, just like for measles, we said 94%. For malaria, is 100%. Because the R naught for malaria is 100, 99.9. So for malaria, is 100. Now, and the costs and economic benefits of an immunization strategy or program. Now, models complement but do not replace local evidence. Models do not replace local evidence. What we are seeing like this, models cannot replace them, but they can complement them. Now, local results, however, may not be available. In either case, decision makers should use modeling results alongside other types of reliable evidence and operational realities to inform decisions. So if you don't have any local evidence, modeling can come in and guide with other available data, reliable evidence, and then operational reality. Models allow for extrapolation beyond a clinical study follow-up period. You know, like you can do a clinical study between January and maybe August. But beyond that, modeling can project beyond August and say, okay, you can see between now and August by your clinical study. But modeling has a goal that can see beyond August by forecasting, by prediction, by projection. Now, generalizability across settings and estimation of clinical lead points from intermediate outcomes. Mathematical models may not always be necessary or appropriate to answer a specific policy question. So that was why I said there are situations where the question may not be answered, the answer may not come from modeling, mathematical modeling. It may come from you carrying out experiments, and then from there you may now go and use model. So model results may be presented in different formats from a variety of settings, such as epidemiological settings, looking at it from that perspective, or spatial in terms of urban or rural settings or geographical areas. Now, it is not possible to know the future impact of immunization strategy before their implementation. It's not possible. But do you know that if I don't have a data and I just want to see if I use a particular immunization or vaccination, how will it be? What impact will it be? If I have a model, I can use my model to understand how the vaccination will play out by simulation. At least by giving me a kind of idea. It may not be the complete exact, but if I simulate, it gives me a graph. You see the graph, the way it's going up and down. Some is getting flat, So before I say that, okay, I even deploy, this is the idea the model is showing. Let's now deploy. And then after deploying, we collect data. We now come back and check whether what the model has said is true or not. We can also do that. So mathematical models can help by simulating or replicating the real world implementation on a computer. Now, models can then virtually test different implementation strategies and estimate their future impacts, or at a fraction of the cost and time, compared with field-based approaches like randomized control trials or maintaining the status quo. Right? Mathematical models are a key source of information for global, regional, or national immunization or control intervention decision makers. The guidance is designed as a resource to assist immunization or control intervention policy and decision makers to understand how to participate in model building. Interpret results from mathematical models, use modeling results in the decision-making process, and use best practices when working with modeling teams. Now, so you find out that you have considerations involved in choosing vaccine intervention. Now you have other non-vaccine interventions here. You have decision on vaccine intervention. So these are the implications. For decision on vaccine intervention, you have disease burden. Now, which give us to decision on vaccine intervention? What give us to decision on intervention, vaccine intervention? One, disease burden, disease epidemiology and natural history, vaccine characteristics, safety, efficacy, duration of protection, costs. Then you have other non-vaccine intervention, e.g. cost, efficacy, public and political demand, implementation considerations, population dynamics, demography, and human behavior. Now, what are mathematical and what types of models exist? In health, models can simulate how disease spread and can estimate the impact of interventions such as vaccination and control programs. Models help decision makers explore possible future scenarios, compare options, and understand the potential benefits and cost of their choices. Now, based on the policy or research, future scenarios may include different vaccine introductions, alternative vaccines or control interventions, and different target age groups. Now, we may want to target different age groups for a vaccine. Like, take for instance, COVID-19. COVID-19 is an age-dependent disease. Now, it gets worsened when an elderly person who has a compromising health, health system, because as you know, for COVID-19, when there are underlying sickness, maybe underlying issues, COVID-19 thrive in that person's system. So you find out that people who are younger, the younger ones in the age, they were able to, to survive with COVID-19, and they came out of it. But people who have underlying conditions, who have compromised health conditions, you find out that some of them battle with COVID-19, some died because they have, like people who have, pulmonary health infection and all that. Some people who have lung disease and all that, they had issues with COVID-19. So COVID-19 is more of an age-structured disease. And that was why in giving the vaccine, they consider different age group and how it works at different age groups. So now models help decision makers explore possible scenarios. Okay, I've said that. Additionally, models can explore different epidemiological scenarios, such as settings with low or high disease burden or with seasonal trends. Models often help decision makers estimate the potential impact of a given vaccination control intervention on health burden, such as disease incidence, number of hospitalization, number of deaths, or costs. Mathematical model represents these dynamics by characterizing the relationship between potential actions and outcomes of these actions. And then these outcomes could include reduction in disease-specific incidence or reduction in disease mortality. Models also help quantify assumptions such as degree of vaccine uptake needed to achieve a desired outcome. Policymakers can then evaluate based on other prior knowledge whether those assumed thresholds are inherently realistically achievable. Now, although this guidance focuses on mathematical models that aim to inform policies, models can also be developed to answer scientific questions apart from policy-driven questions. For example, now these are some questions: exploring the mechanism of an action of a vaccine or immune protection from a disease. You want to explore the mechanism of action of a vaccine or immune protection from a disease. Now, we said the other day now that there exists a vaccine does not mean that it will confer protection. You can give people vaccine, but does not mean that 100% that vaccine will lead to immunity. So you want to check whether this happened. Now, from the point of view of model, insight from this model can be valuable for decision maker. Some types of model, such as multivariable statistical model, can be used to determine association between risk factors and outcome. Right? Now, for schistosomiasis, what are the risk factors for schisto? Anybody? 1, 2. Yes, risk factor. Infected water. Yes. Farming and fishing, right? Yes. Risk factors. Children, young children. Pregnant women, yes. So there are risk factors. And then now we can find relationship between that. And then the outcome of whatsoever happened can find relationship between a particular risk factor and then the outcome. Can find relationship. You know, there's a difference between relationship and association. Somebody was talking about correlation and correlation yesterday, and then regression. Regression is relationship, and then relation is association. Now you may be living in the same house with somebody, right? But you may not have any relationship. Do you understand? You may not have any relationship. So relationship is stronger than association, right? So you may be, maybe you even be in the same class, but you don't have relationship. Are you getting me now? So a stronger way to look at the effect of something on the other is to go for regression beyond correlation. Correlation is surface. Regression is deeper. Okay? So these models can also be used for evaluating vaccination programs. And then the guidance focus on mathematical model for performing prospective analysis. Prospective analysis, that means future. Future. You can see the future from now, given a particular scenario and simulation. Sorry. Now, statistical model versus mathematical model. What's the difference? The key difference between statistical model and mathematical model is that mathematical models incorporate transmission dynamics and simulation. Now, statistical model does not incorporate transmission dynamics. It looks at relationship, association, patterns, and all of that. Statistical model describe past empirical evidence and can be used to forecast short-term trends in data. Now, when we say forecasting, we are talking about between one day, 2 days, 2 days, 3 days to 2 years. That's forecasting. Now, which statistical model can handle? But prediction can be done by mathematical model between 2 years to 10 years. Then you have projection, 10 years and above. That's projection. Now, whereas mathematical models can additionally estimate the impact on long-term future scenarios on the basis of given assumptions. Now, statistical models, they are data-driven. Statistical models are what? Data-driven. Now, I have data. You can't do statistical model. You must have data. But if you don't have data, you can do mathematical model. It should only be a theoretical one. And it can give an understanding. It can give you understanding of what is going on in terms of the spread. It can give you understanding of how the control intervention is changing the patterns. It can give you some light, but that should not be the final. Now, when we now confront it with data, it makes our work to be useful for policy, to guide policy. So they also explore correlation and understand the trends and patterns in data. Now you can use it to, like I said the other day, when you first have a data, the first thing you look at is, let me look at this data to even see its distribution. Let me check the distribution of this data. Like I see many people going to machine learning. The reason why many people are not going to succeed very well in machine learning, a lot of people are doing machine learning, they don't have the statistics. They don't have the mathematics. So when something goes wrong, then it's either you get confused or you leave it like that. You need at least some flavor of maths and statistics for you to do good machine learning. I'm telling you, good machine learning, you need some flavor of mathematics and statistics. Or else, you'll be doing some hallucinated projection. Yes. Some hallucinated projection. You know, some people publish a paper one day. When I look at it, I said, this one a lie. But they are publishing. You know, that you publish it does not mean it's correct. Though. So don't begin to think, we are published. Publish 1 million paper. It's not about that. You may be publishing something that is useless. That's the thing. And one thing about Nigeria is that we love quantity. That's the thing now. I have 1 million paper. But those paper, what are they doing to your life? So it's not just about numbers. It's about quality. What's the content? I told you yesterday, was it the day before yesterday, in China, if you like, bring 1 million paper. Somebody that come around said, I have one paper in nature or science. They will pick him and leave you. Because they knew that what it takes for him to have that paper. No be smart, you know. And for them to accept that paper in that journal, they're a top guy. So it's not just about churning out, you know, people are doing, everybody wants to be machine learning. AI, I'm an AI guy. Artificial intelligence. When you don't have natural intelligence, you need natural intelligence to support your AI. NI, you need NI. You don't know? You need NI. That's why there's need for domain knowledge if you want to find artificial intelligence useful. So you need NI to support what? AI. Plus SI, supernatural intelligence. We'll talk about that one another time. Now, explore correlation. Understand trends and patterns. Then regressions. So you talk about, under that, you talk about, I said something about regression. Regression is about what? Relationship between one thing or the other. Time series analysis. What do we use time series to do? You have been taught yesterday. What primary thing do we use time series to do? Thank you. Yes? Primary thing, use time series analysis to do. Eh? That's not it though. Which trend? Eh? Who is saying that? This doctor is getting something. No? Clap for her. The first thing you use time series to do is to identify seasonal pattern. Seasonal pattern, seasonality. That's one first primary thing. Anything can show you trend. Regression can show you trend. Are you getting me now? You can plot and get trend. I know in social media, I say this is trending. It's trending. Everybody's, you know, so, but seasonality. You want to see the seasonality. Eh? What is seasonality? That's another second question. Yes, seasonality. What is it? Don't mention disease. Just say upward and downward. Yes, I know. This man is a mathematician. He's using the mathematical something. Okay. Okay, so what of cyclic? So what's the difference between cyclic and seasonal? Cyclical and cyclical and seasonal. Yes? Eh? No, that's just a trend. Okay, that same time, yes. So what does it? So there are two things that I wanted to mention that you have not mentioned to me. One is, No, there's something you are missing there in that regularity. Yes? Okay. No. You didn't get it. It's not as it can go beyond a year. That's why we said is what? It's regular and repetitive. That's what you note. Do you understand? Regular and what? Repetitive. That's seasonality. For cyclical, it's regular, but it's not repetitive. Now I'm seeing a peak in August 2025. Peak, the same peak, 2024, August. The same peak, 2023, August. Is regular, is what? Repetitive. But when you see cyclical, it's regular but not repetitive. It's not at the same time. Do you understand? It may be August, then March, then another time of the year. So that's why that's the difference between cyclical and what? Seasonal. I'm rounding up. Use for nowcasting. You can use statistical model for nowcasting. When Ebola started, they asked us from African CDC, can you help us see what is going to happen in the next few weeks? We plotted it. That one, just one of our codes that we have used before. Just plotted in the next 7 days. This is what you will see, and we gave the bound and the lower bound and the upper bound. And when it came, it fell within that. So you can do nowcasting in the next 1 week, the next 5 days, forecasting within 2 years to predict the current epidemiology where it might be in the next few weeks. That's why people in public airspace need to be empowered with this kind of thing. They just call you now. They say, disease, we have gotten the data. Can you show us where it will be in the next 5 days? Because they want to make a plan. Maybe the number of beds we should provide in case there is more severity. The statistical models may also be used to estimate the efficacy that is of a particular vaccination. We want to estimate it, and effectiveness of current treatment and prevention measure, and use it to do that. I'll stop here today. Thank you very much.
We want to appreciate Prof. Demore. Thank you very much, Prof. It's been a loaded section, and for me, one of the key points in this session is that modeling cannot be done in isolation. You cannot just be in your office and then say you want to model, you're just in your office and then you're modeling. You want to do modeling work that will be used to inform policy. It has to be what? It has to be done what? Collaboratively. With who? With which experts? Prof mentioned some of those people we need to collaborate with so as to do policy-informed model. We should do what? Collaborate with who? Epidemiologists, health experts, who else? Statisticians.
I thought you said politician.
Yes, we may also need to
policymakers
collaborate with some politicians.
It's so that
policymakers.
Can bring body out for that.
Because they are the ones deciding, they are the decision makers. So we also need their collaboration. All right. So any question?
questions. Let's take some questions for Prof. Questions. We are taking the numbers now. 1, number 2, and then number 3. All right, so let's go quickly.
Prof, thank you very much, sir, for the session. So I have 2 questions. The first one centered around reproduction number and the other one on parameter. So just like you have said that for some diseases like measles, we know their reproduction number. Now, there are so many times someone will come up with a model of measles, for instance, now, and the reproduction number somebody will get in that instance may not be in that range. Some person may even be getting like 30. I'm just using an instance. So at what point will you know what went wrong? And at what point can you be able to validate reproduction number for other diseases that probably you have not worked on, so that if you are trying to come up with a reproduction number, you know what exactly it could be? That's the first one. And the second one concerning the parameters. So in the course of our model, we have some parameters that we can estimate, but for those parameters that you don't know values for, how can you come up with possible guess such that that guess can be right on the long run, so that it can also be used to make informed decision?
All right, thank you. Now, number 1, the problem with mathematicians is that they just want to model and publish. Now, but the thing is, you want to enter somebody's field and then you don't want to understand what obtains there. You are going to fall. Now, we are working on measles. Measles is not a new disease. Now, when a disease have just started, that's where you can calculate it out or not. But when it's already established, when it's already persistent, when it's endemic, you don't talk about how not anymore. You are talking about its effective reproduction of, because there is intervention, right? So if you find a paper writing measles and is saying that you want to calculate how not, it's just, that was what I was saying. It's just somebody wasting his time, because these guys are not informed. Now, before you go and work on any model, you should study the epidemiology of the disease in terms of what is the R0 of that disease, what is this of the disease, do we have the R0 calculated already? So when you are informed about all that, transmission, immunology, everything about that has to do with the biology of that disease, it gives you a first-hand information. And it guides whatsoever you are going to put in your model parameter, your model formulation and all that. But in a way where you just pick a paper, maybe a modeling paper that is even wrong paper, and then you are writing the paper and the person got R0 as 50 for measles. The paper is already a confused paper. So, I mean, you cannot use that kind of work to do any meaningful thing. You cannot use a bad paper to produce a good paper. Are you getting me now? So, now you need a good paper to produce a better paper. Are you getting me now? So, the other one on parameter. Now, in a modeling, you did parameter model fitting and parameter estimation yesterday. Now there are certain parameters that you don't know about, they are known, right? They are known. One of the things you can do, first of all, do your good literature search. Not from modeling paper. I've been warning you. Don't start your work in modeling with a mathematical modeling paper. You have shot yourself on the leg. And you have limited yourself. Start with biology, epidemiology, public health things. Start with there. Start with that. Get to see what people have done in epidemiology on maybe measles, for instance. And then get those publications in different countries. It will give you information about what the parameter can be. Now, if you are now working on, if you say that parameter is a rate, you know that your guess should be between 0 and infinity. If you say that parameter is a proportion, you know that your guess should be between 0 and 1. Do you understand me now? Those are the things that we should give you understanding first. Are you getting me now? So that's why you cannot do modeling without having a taste of functional analysis. You can't do modeling without having a taste of optimization. You can't do modeling without having a taste of some level of algebra. Because like I tell you that 0 to infinity is just R plus. Then the set of positive real numbers, right? So it means that my rate falls within that. Are you getting me now? So now the literature you have read will give you understanding that these are the biology interpretation of what's it called? Maybe latent, you understand, infectious period. Good papers, and then from there you build up. Then another thing is also that if you are working on a data, you need to now put some seasonal pattern and all that. You also need, I mean, those ones are the major ones you should estimate. And for your information, by standard, you should not estimate more than 5 unknown parameters. When it's more than that, you will find yourself in trouble. Yes.
Yeah, thank you, Prof, for this insightful session. One of my questions, I think you've tried to answer it a bit, though I may still ask it. It's on the comment you made that because we are learning machine learning, but you said we can't really do good machine learning without having
some flavor.
Yes. So flavor of statistical modeling and molecular modeling. So I would like you to throw some lights, maybe give some practical examples for us to really get the flavors you are referring to.
Okay.
That's one question.
Okay. That's one question. Number 2.
Okay. My number 2 question, it does escape my head, but my number 2 question. Okay, yes, I remember. So it's on cyclical data that you
cyclical pattern.
Sorry, cyclical pattern. Yes. So I need you to throw some light on it because I'm trying to grasp, have a grasp of it because it seems like, because in my current knowledge of data analysis, I feel once any data is not, doesn't have a pattern, doesn't have a seasonality, I would easily say, it's just a random stuff. So maybe throw light so that we can see maybe what sense it can make from such cyclical pattern that is not repetitive or something of that nature.
Okay.
Thank you.
Yeah. So like now you have a data. You are a machine learning person. You have data. And then now one major thing as a machine learning person is that you must understand the science of data or that data. If you don't understand the science of the data, when data is misbehaving, you don't know what to do. Now, how do you understand the science of data? If you have some flavor of statistics, starting from being able to identify variables, being able to identify, different kind of variables, names and stratifications and all that, being able to know some basic statistical tools to answer simple statistical questions. Now, it's very important because you will find yourself every time seeing patterns. When you see machine learning, you are seeing different kind of patterns that you yourself cannot explain because you don't have the statistics. So that's why, you see, the problem we all have, generally, when you find people in medical, in biological science, in physical sciences, is because the maths and the statistics we learned was not taught as to answer questions based on our needs. Let me give you this. Now, you will see in America, when they are teaching students mathematics, they teach them both theory and its application. So if you are from primary school, secondary school, they find the applications. Now, so everybody start developing interest in mathematics based on where they want to, the course they want to do. Do you understand? That's the way. So if I find applications from in law, even though you are in law, when you are doing the maths from day one, you are seeing how maths can be applied in law. From day one, you are tuned to mathematics. That is a useful tool for me, even though I'm going to be in law. Now, somebody in medicine, right from primary school, is seeing its application live. Now, the person will train himself to maths immediately. You will not say maths is abstract. No. So the problem we have is that from day one, you just see maths as, let me just CCs and pass it and what? Go. When you get to university and you see me the maths again, MTH 101, 5 units. If I can get C, at least C, let it not spoil my results. Go. So you will just go and sit down with one tutorial master and you'll be solving the question and you are cramming everything. Once you get to the exam hall, the day you just pour it down. That's all. From that day, you don't even know anything. If they ask you what is sword, they was we sword. Okay, about that one. You don't know anything because you are finding it useful. So that's where the problem starts. But if it has been that now you are doing statistics and mathematics from cradle to university and they are showing you applications. Are you getting me now? By now, if you are eventually find yourself in machine learning, you already have some basic statistics that can help you. So the Nigerian education has that comma, yes, deficiency, which by the grace of God, we in Ikamda, we are trusting God to do the campaign. Now we have a plan. I have a plan that between now and December, I want to host mathematics teachers. Yes. Starting from Oye Ekiti. Just maths, 50 maths teachers. And what do I want to do? I want to flush their brain. Yes. If God provide me, just 1 or 2 days meeting, if God provide me, I know God will provide me money. You will sit down, you will eat good jollof rice. You will not pay any money. Just come. You will eat good jollof rice, give you nice meal, make you to sit down, relax. You know the way they suffer teacher in Nigeria? You feel relaxed. Then I bring these truths. And then gradually we begin to change how they teach mathematics going forward. That's the vision I have. Are you getting me now? So we want to start correcting it from now so that the coming generation will not enter the same trouble. And we'll take it straight to the state government. That's the plan. But it will start like a seed. But we have that plan. I hope I've been able to answer your question. The second question was on cyclical, right? So now, when you have a data, especially a time series data, the first thing you do is to carry out decomposition. To decompose that data for you, to see it in terms of seasonal. Does it have a seasonal pattern? Does it have a trend? Let's look at the trend. Is it an increasing trend or a downward trend? Do you understand? It makes you know the pattern of the data. Is it a downward trend or an increasing trend? So, and then it shows you seasonality, it shows you the cyclical pattern. It also shows you the remainder, which is more random. That means the error in the data. Now, the reason for that is because now when you have a data, when you are looking at it like this, you don't know what that data is until you decompose it. It's like fractional distillation of crude oil. When you see crude oil like this, until you take it through fractional distillation, that's when you take out petrol, diesel, everything that you don't know, gas, bitumen, all of those things will come out. That's what we are doing. So when you do that, it shows you, okay, this is a pattern of this data and all of that. It gives you information about the data going forward. Are you getting me now? So that information will guide many things about what you are going to eventually do with the data and how you will interpret the data going forward. Okay? Next question.
All right. So you said you've addressed this question. So we want to take some online questions. So the first question online.
Sorry, sir, hold on.
Okay, is the person talking?
There's someone that is raising his hand on the
Okay.
call.
Hello.
Write it.
You already tell me.
Hello, please, can I be heard?
What's his name?
Can you hear me?
So,
Can you hear me?
speak now. Speak now.
Hello? Hello? Hello?
Please ask your question, please.
I don't know. Can you hear me?
Yes.
We can hear you.
Okay, okay, good. So I wanted to know the difference between a probability parameter and that of a rate. Thank you.
The difference between what?
A probability parameter. A probability parameter
Probability
and that of
parameter.
a rate. Yes, yes.
And what?
And a rate, a parameter that is measured in rate.
A range. Oh, okay.
Rate,
Now, so
rate.
when we say probabilistic, it means that it's proportion. It could also be that, I don't know, if you want to make me take it further, it could also be that you have induced stochasticity on that parameter. You know, stochasticity is based on probability. So you have induced noise on the parameter. That's one. And then you want it to show some random fluctuation. But that's one way.
Yes, please.
Another way is that the parameter you have chosen is between 0 and 1. So, but if it's the other way around, when you have a rate can be in a range between beyond 0 and 1, can be between 0 and infinity, positive infinity. Did I answer your question?
So let's take the second question online.
All right, sir. So this question is from Jeremiah Omojirigbe. He says, the virtual group are planning to work on a modeling project with the details below. We would like to receive your suggestions, advice, and how we can achieve this. Currently, we are at the methodology stage, trying to explore model possibilities. Topic, developing models that integrate clinical, genomic, and epidemiological data for malaria forecasting. Proposed objective. The objective of this study is to develop and evaluate an integrated predictive modeling framework that combines clinical, genomic, and epidemiologic data for malaria forecasting. So he's asking for your suggestion, advice, and how they can achieve this, sir.
Yeah. So the question is, your objective is not well defined. You have missed objective with methodology. That's number one. Number two, combining genomic data with epidemiologic data would be a good stuff, but we need to know what time period are you looking at, and the genomic data. I mean, what time period did you take the genomic data? You may need to know so that it's not as if you are doing something that does not follow the same set of period. So I think those are very important information. But you can get me online. I'm part of your group. So we can discuss further on that in that group. Thank you very much.
All right, sir. Can we appreciate Prof? Thank you very much, Prof. So we have come to the end of the first session. We'll be going for tea break before Professor Tron comes up. So quickly, we'll go for the next 15 minutes to have our tea break. So we can go now, but it's not compulsory if you don't want the tea. So Prof said you can